Alrighty, well, hello everyone. Welcome to chapter 9. In this chapter, we'll be talking about center of mass, first of all, and then we'll be moving on to conservation of linear momentum and collisions. Alright, so this should be the first video in this chapter. And so we have to talk about a concept called the center of mass. And as you may suspect, it's pretty much what the name implies, right? You have a mass of some shape, right, and some mass, and we want to find the center point, right? Now, that being said, we won't necessarily talk about one single solid object and compute the volumetric single or center of mass. We'll primarily be talking about the multiple masses and trying to find the center of mass among the system. So it'll be somewhere in space, okay, in between them. Although there will be problems where you'll have, for example, a sheet, right, a 2D sheet of some area, and you want to find the center of mass of that sheet, right? So this process will apply to that process as well, right? The process for finding the center of mass for two point particles, for example, here and here, is the same as if this was a solid continuous object, okay? Now, the question we want to ask ourselves when finding the center of mass is, well, not only where the center is, but what are we trying to find, right? At the basic level, what are we trying to find? Well, we're really finding an average, right? The average position of an object's or a system's center of mass. So in this case, in this system comprised of 2 point particles, let's do it like that, right? For right now, let's say that they both have mass m, right? And they're separated by a distance we'll call d, okay? And so intuitively, right, at first, where would you think the center of this system is? If you said halfway in between, right, or midway, you're correct. But there's a certain process of finding that, right? That's essentially the average position of both of these if they're equal mass, right? Another way to say that is that this mass pulls the center point, right, the imaginary intangible point, just as equally towards this mass as this mass over here pulls that point towards it. Right? In other words, the average is right in the middle. Right? What would happen if one of the masses had more mass than the other? Right? 2 or 3 times more. Well, that center will shift. And let's see mathematically why, right? Or how. So, what we want to do is effectively break this space up into equal segments, right? And so if we do that, well, we have two halves, right? So the location of the center of mass, which in this case we'll just call xcm, I'll call this the x-axis. If this is the average position, that means we want to end up with a unit of distance, right? We're finding the position here, not the average mass, but the position. However, these objects in the system have their own mass, whatever that is. So if one of the objects has more and more mass than the other object, that will affect the position of the center of mass of the system. So we have to incorporate both mass and a distance. And so let's put the mass of the left one, right? And that comes with its own, we'll say, position in space. I'll mark that by x1. And then added to that is the mass and the position of the right particle, right, of the other mass. And that's all we have. That's all we're worrying about right now. So let's divide now, just like an average, right? Remember, this is basically an average. So we have to divide by everything, right? In other words, by all of the mass. So the left mass, m, plus the right mass, m. Okay? And if we do this, look at the units, right? We have, I know a mass times a distance is not very intuitive, right? It's not. So just ignore that part. But look overall, right? The units are kilograms times a distance, right? Or mass times a distance for both terms. And on the bottom, it's just a mass, or just kilograms. So that means that the units of kilograms will cancel on top and bottom, leaving just units of distance. Okay? So that's the first thing. The second thing is this x1 and x2, right? Where is that being measured from? Right? That's a question you'll need to ask yourself. I haven't determined that yet, right? I haven't chosen that yet, so it's time to do that now. Let me choose this point right here, right? Let's choose the location of the left mass. I'll choose that to be, if that's the x-axis, right? That's 0, okay? In other words, x1 equals 0, okay? So that means that the first term effectively goes away. And we just have m times x2 divided by the total mass of this two-particle system, which is 2m. And now can you see what's about to happen? The mass, which I'm just calling m, cancels out, and we're left with 1/2 times the position of x2. Well, x2 is being measured from 0, right? I set that to be 0. I'm free to do that. And so that means x2 is the same thing as d in this problem. So in other words, the center of mass is located at a distance of 1/2 d. In other words, let's do it, just cm, right there, in the middle. Okay, and that's our answer. That's our answer when measuring from the position of the left mass, okay, when putting 0 at that position. Let's do it from putting the, let's do it again. So let me do something real quick. Copy. Haha, I love that feature. Okay, let's line it up again. And now, instead of putting 0 there, let's put 0 at the position of the right mass. So that's 0, okay? We're only worried about distance in this case. So xcm, let's do the exact same process again. We have both masses we need to take into consideration. So the mass of the left particle times the position of the left particle, which I guess I'm calling 1. And then we're adding the mass and position of the right particle, which I guess I'm calling 2, divided by the total mass, which is still, I'll write it now as 2m. Okay? And since I've set 0 to be the location of the right mass, well, that means x2 is 0. I guess I should cross that out up there. Right? And so we have pretty much the same thing as above. Now, m cancels out, right? Remember, m is just a variable, so that can be any number. And so we have 1/2 x1, which is the same thing now as d. Yes, it's going the other direction, but distance-wise, d is some distance. It's the same distance from the second particle here as it was from the first particle. Okay? You can put a vector on there if you want to, right? Say going right is positive and left is negative. You can do that if you want. And in fact, let's do that really quick. So let's say to the right is positive, and that's negative. Okay, that means when we evaluate the numerator, in this case, x2 will still be 0, but x1 will equal negative d, right? Because you're going from 0 this direction, right? That's the location of mass 1. You're going left, which in this case I said was negative. So that means you would put in a negative distance, and thus you get a negative 1/2 d. Okay? So let's do it one more time. But now let's do it, instead of masses being the same, let's do this. Let's make them not the same. Let's say that's 2m, right? Let's put the 0 position, tell you what, let's do it. Let's do it from the middle. You want to do it from the middle? Let's put 0 halfway in between, right? So now, doing the same exact process, we have the mass of particle 1, in this case m, the location of particle 1, which I'll call x1, and we're adding to that the mass of particle 2, which is 2m, and the position of particle 2, which we'll call x2, divided by the total mass, which is m plus 2m now. Okay? And so here, let's put in a direction. So let's call that positive and left is negative. Now we have m, and then x1 is at a distance of negative d over 2, right? And then we're adding to that 2m, and x2 is at a distance of positive d over 2. And we're dividing by 3m in total. Okay? We're getting there. So canceling out m, we have negative d over 2 plus 2 times d over 2. Well, that's minus d over 2 plus d all over 3. And I'm running out of room very quickly. Thus, we have positive 1/2 d, right? And here, flip and multiply, we have, whoops, that meant to be an equals. We have d over 6 as our answer here, right? And so this should make sense, because if we're thinking of this as an average, well, the sum of masses, we have 3m, splitting that up into 3 sections, right? Meaning we have 1 section, 2 sections, 3 sections, right? Into thirds, in other words. Well, that means that this distance here is 1/2 of that, right? So now the position of the center of mass is no longer in the center, it's exactly right there. It's 1/6 of the distance between them, but towards the more massive object. Okay? So, in essence, the equation for the center of mass, right, or rather the algorithm, is 1 over the total mass, and then we're multiplying by the sum of all of the masses and all of their positions. Right? So we're using summation notation here. Okay? And it doesn't matter if you just have 1 particle, 2 particles, or 18 particles, right? This algorithm here will give you the position of the center of mass, right? Because notice the masses themselves will cancel. All right. I should note that, real quick, if we have the masses themselves, right? So from earlier, m and m here, and they're separated by a distance, right? If these masses were to move, right, say they go over there to a new location, right, we'll call x1 prime. This mass was to go, I don't know, wherever, somewhere like that, right? Wherever it goes to x2 prime, right? That takes some time to happen. And so we have a change in position, right? Or a change in displacement, rather. Well, that means that we really have a change or a velocity, right? Those particles have some velocity in that case. And so does the center of mass. So the new center of mass will again be halfway in between. So that would be xcm prime, like that, right? And so what we have here is effectively the following. Let's do the sum, right? I'm just rewriting the equation above. And what we have is if this were to change in time, right? The ddt of this, well, that means we have total mass times dx dt. Well, that's the same as speed or the velocity, right? And that's the velocity of the center of mass. And so the same thing on the other side, right? So this is defined as the momentum, right? The momentum of the center of mass. M times V is equal to momentum, which I'll speak further about in later videos, right? But this leads into the impulse momentum theorem that you'll see in later videos as well, right? Because as these positions change, you can just take the time derivative of this as well, and you'll get the impulse momentum theorem, right? But I'll show that in the next video. That's it for this video. Thanks for watching.